Hello, everyone, and thank you for the invitation. My name is Marina, and I work at Piston.
Marina, maybe a bit louder, so I don't know why, but your voice is not so clear.
Now, do you hear me?
Are you here, Marina?
I try to provide a response.
Okay, yes, I think it's okay. Yes, sorry.
So I'm from the Institute of Solid-State Physics and Ventspils International Radio Astronomy Center at Ventspils University of Applied Science. And today I will present our work on the numerical modeling of hydrogen compression using the liquid piston concept. This study is based on multiphysics simulations performed in COMSOL-Multiphysics. As all you know, hydrogen is one of the most abundant elements on Earth, and it's widely seen as a key energy carrier for the clean energy transition. And it's especially important for sectors that are difficult to electrify. For example, heavy industry, long-distance transport, and maritime applications. Hydrogen also enables energy storage from renewable sources like wind or solar power, helping to balance their intermittent nature. For this reason, hydrogen is strongly aligned with the European Union's goal of achieving climate neutrality by 2050. And it's expected to play a significant role in future marine and maritime energy systems. However, the use of hydrogen at sea comes with specific challenges, particularly in terms of storage and compression, which require safe, efficient, and cost-reliable compression technologies. On this picture, you can see a typical hydrogen compression infrastructure from production to high pressure storage. And hydrogen can either be delivered to the site or produced also locally using electrolysis and often powered by renewable energy sources as wind or solar. And in this case, we usually refer to green hydrogen, which does not produce CO2 during production. After production, hydrogen needs to be compressed from low or medium pressures to the high pressure levels and required for storage and distribution. This compression stage is key part of the overall infrastructure. In marine and maritime systems, the same concept applies, but of course, additional requirements appear. Equipment needs to be compact, reliable, and suitable for offshore conditions. This slide shows the concept of a hydraulic hydrogen compression system based on the liquid piston principle. This compression concept has been developed by our research group at Ventspils University of Applied Sciences and is protected by several national and European patents. In this system, hydrogen is compressed in several stages using a hydraulic working fluid. In our case, it is silicone oil, which acts as a liquid piston. The use of liquid piston allows smooth and well-controlled compression. The system includes primary and secondary compression stages, high pressure storage, and set of valves that control both gas and fluid flow. One of the main advantages of this approach is a relatively small number of moving parts. Also low noise levels and improved thermal management. And in general, this system can reach pressure of up to 100 megapascals. That making it suitable for port infrastructure and offshore platforms. This slide summarizes conventional mechanical hydrogen compression technologies such as reciprocating piston, linear, and diaphragm compressors. And all technologies are well established and widely used in stationary and automotive applications. they can achieve high compression pressures and have proven performance. However, when we move to marine and offshore environments, some of their limitations become more pronounced. Mechanical compressors typically involve many moving parts, which leads to higher maintenance requirements as well as increased vibration and noise. And as a result, conventional mechanical compressors are not always, let's say, the optimal solution for marine hydrogen infrastructure. And this motivates the search for alternative compression concepts that can offer a little bit simpler design. Here you can see the alternative solution. And in this liquid piston concept, in this approach, hydrogen is compressed by a liquid column that acts as a piston inside a fixed volume chamber. And this allows the compression process to be smooth and also well controlled, while avoiding many of the mechanical issues found in conventional compressors. An important feature of the liquid piston is its thermal behavior. The liquid absorbs heat generated during the compression and can be cooled more effectively. And as a result, the overall compression efficiency can increase from typical value of 17% to over 85%. To better understand how hydrogen behaves during compression process, we use a numerical model. This allows us to study how pressure and temperature change during the compression process and to design a more safer and more efficient system. One of the main advantages of simulation is that the different operating conditions can be tested without physical experiments. We can change compression speed, the geometry of the chamber, or working fluid, which saves the time and cost and helps improve system performance. Here you can see the model. It has height of 145 millimeters and a diameter of 100 millimeters, and the total volume of little bit more than 1 liter. Hydrogen is located in the upper part of the chamber, while oil acts as a working fluid below. As the oil rises, the hydrogen is compressed. The simulation includes heat transfer between the hydrogen, the oil, chamber walls, and the surrounding environment. And this multiphysics approach allows us to analyze temperature variation, heat losses, and pressure development during the compression cycle. Here you can see liquid piston compression chamber that was implemented in COMSOL software. We used, as I talked previously, a multiphysics approach that combines compressible gas flow for hydrogen, incompressible flow for the liquid piston, and steady heat transfer. The model includes all the main parts of the system: the hydrogen region, the liquid piston, and of course steel chamber walls. During compression, the gas and liquid are compressed together, and heat transfer between the hydrogen working fluid and the chamber also is taken into account. This allows us to analyze how pressure and temperature change during the compression cycle. In COMSOL, implementation begins with model parameterization. All key parameters are defined in the global definitions section. This includes key geometric values such as piston stroke, cross-section area, and compression chamber height, as well as initial conditions. Defining these values as global parameters mean that the same values are used consistently throughout the model in geometry, in physical interfaces, and study signals. The next one slide shows that we set the initial conditions using global variables. This includes the initial pressure, the initial gas, volume, the mass of hydrogen in the compression chamber, and also compression time. The key point here is that the gas volume and density are described by time-dependent expressions. This allows us to represent the compression process continuously rather than a series of discrete steps. And in this way, the thermodynamic behavior of hydrogen is directly related to the geometry and motion of the fluid. In the next step, we determine environmental conditions, such as temperature and pressure. This allows us to account for heat exchange between the chamber walls and the surrounding environment. This allows the model to include realistic heat losses, which is important when analyzing temperature change during a hydrogen compression process. Model geometry. Here you can see the geometry of our model. We use a 2D axisymmetric model, which is well suited for this type of cylindrical system. The chamber is divided into three regions: hydrogen domain, still chamber, and liquid piston. And this configuration is sufficient for realistically studying compression and heat transfer effects. Besides building the model directly in COMSOL software, the geometry can also be imported, for example, from the SolidWorks. This slide shows how material properties are defined in COMSOL model. Material parameters are defined for all regions. We define key physical properties such as thermal conductivity, heat capacity, viscosity, and density, which directly affect both heat transfer and fluid flow during compression. And these properties are used consistently across all associated physical interfaces. You can use materials already available in COMSOL software, or also it's possible to enter them manually. This slide shows the physical properties of the material used in the model. For hydrogen, we use standard thermodynamic properties such as molar mass, heat capacity, and heat capacity ratio. These parameters are necessary to describe the change in temperature and pressure during compression. The liquid piston is characterized by thermal conductivity, density, viscosity, and heat capacity. This slide shows how chamber geometry and piston motion are implemented in COMSOL. The fluid piston motion is achieved by moving the boundaries using the deformed geometry feature, rather than moving the entire mesh. This approach allows for smooth changes in gas volume during compression, while maintaining mesh stability and avoiding mesh rebuilding at each time step. And as a result, we can accurately track the compression process with good numerical stability and reasonable computational costs. This slide shows how heat transfer is considered in the COMSOL model. For all major parts of the system, hydrogen gas, liquid piston, and chamber walls, during the compression, heat is generated in the gas. and partially absorbed by our liquid piston. In the model, volumetric heat sources are defined within the liquid regions, and appropriate thermal boundary conditions are applied to the chamber walls. And this allows for the description of both heat generation within the system and heat loss to the environment. With this setup, COMSOL solves the coupled problem of fluid flow and heat transfer. In COMSOL, hydrogen is described as a creeping and compressible flow. Due to these low velocities, inertial effects can be neglected without loss of accuracy. At the same time, the compressibility of the gas is fully preserved. Since pressure change during compression are the key physical effects we want to account for. The isosymmetric formulation further simplifies the problem while maintaining the correct flow physics. And taken together, this approach provides a stable and physically consistent description of hydrogen behavior during the compression stroke. The motion of a liquid piston is implemented in the COMSOL model in the next way. The liquid piston is not modeled as a mechanical component that I have already mentioned, but this component moving inside instinct, its motion is driven through a moving boundary at a specific velocity. This boundary represents the interface between the liquid and gas and moves upward during compression. And as a result, the gas volume continuously decreases, making the compression process controllable and physically consistent. A significant advantage of this approach is its numerical stability. Since the mesh itself does not move or deform significantly, remeshing is not required during the compression cycle. Here you can see the mesh in the COMSOL. The finite element mesh is generated for the entire computational domain, including the hydrogen region, the liquid piston, and the chamber walls. To ensure sufficient accuracy, the mesh is locally refined near the solid-liquid interface, as this is where strong velocity and temperature gradients are expected. Specifically, boundary layers elements are applied along the all chamber walls and in the region of the moving liquid piston. This mesh design allows for the correct consideration of both flow and heat transfer effects without excessively increasing the overall number of elements. And as a result, this achieves a good balance between numerical accuracy and computational efficiency for simulating transient compression. The model uses a triangular finite element mesh. In the hydrogen region, the mesh is relatively coarse, as the flow is smooth and the velocity are low. But at the same time, the mesh is locally refined near the interfaces between the hydrogen, the liquid piston, and the steel walls. These regions are crucial for resolving heat transfer and boundary effects, so boundary layers elements are used there. As the liquid piston moves upward, the hydrogen volume decreases step by step. The mesh smoothly deforms with this movement, following the change in gas volume without restructuring. And in total, the mesh contains approximately 21,000 elements, providing a good compromise between numerical accuracy and computational cost for unsteady state simulation. We used the time-dependent study. The simulation type corresponds to the specified compression duration, and in our model, the longest compression was 20 seconds, and the faster 0.5 seconds. All physical processes are solved in a fully coupled way. This includes the flow of compressed hydrogen, the movement of liquid piston through the deformed geometry, and heat transfer in gas, liquid, and chamber walls. This model allows us to track continuous change in pressure and temperature during the compression process. After running the model, we obtain results and can review and analyze obtained data at each calculation step. The average temperature is calculated separately for each region: the hydrogen gas, the liquid piston, and the steel walls of the chamber. This allows us to clearly separate the thermal behavior. By examining average values rather than local peaks, we can trace general heating trends during the compression process. This analysis is particularly useful for understanding the role of liquid piston as a thermal buffer and for assessing the efficiency of heat transfer to the chamber walls. And this information also is important for optimizing the compression rate and geometry of the chamber. Once the calculations are completed, we can calculate the average temperature in each domain. You can see the temperature, for example, at 5, 10, and 20 seconds. We can see also the average temperature results for any time period. This slide shows the temperature distribution inside the compression chamber at different points of time. On this slide, the results are presented for three characteristic times: 3, 10, and 20 seconds. During the early stages of compression, the temperature increase is primarily concentrated in the hydrogen region as the gas is compressed by the liquid piston. As the process continues, heat is gradually transferred to the liquid piston and then to the steel walls of the chamber. And this becomes more notable after 10 and 20 seconds. And also, these graphs clearly illustrate the transient thermal behavior of the system and show how the liquid piston and chamber walls contribute to the redistribution and removal of heat during the compression. Thus, the process occurring during a single compression stroke was simulated using the presented model with compression stroke time varying from 0.5 to 20 seconds. The initial hydrogen and oil temperatures were set at 300 Kelvin, and the compression ratio was equal to 5. The calculation results for two scenarios are shown here, and one with an initial gas pressure 3 megapascals and another one with 20 megapascals. Figure 16 shows the temperature field distribution within the cylindrical chamber. The figure shows the variation of the gas temperature over a 20-second stroke at time interval 0, 10, 15, and 20 seconds. And these results highlight the significant heating effect within the gas as compression progresses, especially at high pressure. Figure 15 shows the temperature change over time during a single compression stroke for hydrogen or working fluid and chamber walls at initial pressure of 20 megapascals and compression ratio 5. a lot of time, maybe about results. The results of the compression process simulation allow us to estimate the temperature increase of the gas and the working fluid, in our case, is liquid oil, and therefore determine the energy expended during the compression process. On these figures, you can see how the average hydrogen temperature and oil temperature changed during one compression stroke, depending on the initial pressure in case of 20 and 20, 15, 10, and 3 megapascals. Here you can see the temperature increase predetermined in the model corresponds to the energy expended in the hydraulic compression process of hydrogen and stored in the hydrogen, oil, and cylinder body in walls. The amount of energy stored in the compressed hydrogen, oil, and steel is determined using an equation based on the laws of thermodynamics. Here you can see energy distribution at initial pressure of 3 and 20 megapascals. And this diagram shows that most of the energy is concentrated in hydrogen during the compression. But of course, under real conditions, hydrogen and oil mix and exchange heat. When mixed, the gas cools and the oil heats up, resulting in a more balanced overall temperature regime within the chamber. This slide shows temperature change for varying compression stroke duration at initial pressures 3, 10, 15, and 20. The next one slide, it shows the relationship between the power required for compression and the duration of the compression stroke for 4 different initial pressures. Results link. Figure 24 shows the increase in hydrogen temperature at different compression chamber heights. We have changed height of the chamber. The results here really illustrate how chamber geometry and compression duration affect the thermal behavior of hydrogen during the compression. On these figures, you can see that the chamber size has a significant effect on temperature change at low volume, but eventually stabilized. And these trends suggest that while large chamber volume contribute to greater heat release, their effect diminishes at higher volumes, indicating an upper temperature limit beyond which increasing volume has little effect on temperature increase. I will skip this for this because it will be a conclusion. And conclusions. In conclusion, it should be noted that numerical results demonstrate that liquid piston compression provide effective thermal management during the hydrogen compression process. And chamber geometry significantly influence both temperature and energy consumption, making the optimization necessary. Due to their compact design and favorable thermal characteristics, liquid piston hydrogen compressors are well suited for use in the marine and offshore hydrogen industry. So thank you for attention. Are there any questions?
Thanks a lot. Any questions, comments? Yes, we have question from Norman Jacobson. Norman, can you come, please? Down. Excuse me. Did I get correct? Then you are
your compression cycle is about 20 seconds. Is it like that?
We can change. We can start from 0.5 until 20. Yes, but on this result, you saw that we compare how this compression time depends on pressure.
Okay, half a second is faster and 20 is slower. I'm just wondering about and how high, what is the height of your, how long it is your cylinder?
145 millimeters. It's very small, 1 liter.
So this velocity is well below 1 meter per second in any case, average. So, but then my question is, you are using boundary finite elements. Boundary finite elements is usually used for boundary layer to reveal boundary layers, as the physicist Frankl introduced them in the previous century, beginning of previous century. And do you think this is really needed to use boundary layer elements in the case when your velocities are so low? Because this can be avoided.
It's a discussable questions, and because we have no mixing between our domains. Yes, it's separately hydrogen and liquid piston. And maybe I needed more that when we developed this model, our local Latvian Process Analysis and Research Center helped to us to create this model, because it's very tricky in this in total to model a compression process. And they decided, they help us to create, and they help this mission, and they offer.
Okay, that was their idea, to put boundary elements on the MarTe walls.
I will fix this, and maybe we are planning to continue our modeling, so maybe we will something to change and improve our model.
Yes, I would like to suggest to do the same modeling without boundary elements and check what is the difference. I don't know, maybe it has something else which I missing, which I didn't see at the moment now, but my suggestion is to do without them and see, did you have different solution? Thank you very much.
Thank you very much. Yes, I will be really use your recommendations.
Thank you. Thank you, Norman, for comments. Yeah, actually, in this case, we have different kind of speeds, because minimum speed is 0.1 second. So and compression speed would be several, even 10 meters per second, even more. But yeah, so we will try to investigate this as well. Thanks, Marina.